So, well, and thank you for joining us in another WEG Automation webinar. My name is Leonardo. I am the Automation International Sales Supervisor for Low Voltage Drives and Controls, and I will be your host for today's event. I am located in our factory in Jaraguá do Sul, here in south of Brazil, and with me we have our whole sales team ready to support us during the presentation. Before we start, I would like to inform you that during this event, your microphones will be muted, but you can interact with our team through the questions and answers chat that is located on the right top corner of your screen. We will be answering your questions along the presentation, and at the end, we will also leave the chat open for further questions. This webinar has an estimated duration of 1 hour. The recording of this event will also be available and you can access it at any time using the same link on the invitation you have. At the end of the webinar, we will share with you a link where you can find the presentation and all other medias that we're going to use on this presentation. Uh, Pumping systems powered by electrical motors are widely used all around the globe and are responsible for a considerable part of the world's electrical energy consumption. There are many advantages of using VSDs in pumping application, such as energy savings, improved performance, and reliability in the system. Today, we will address some of these topics. I would like to introduce you the speaker for today's webinar, Mr. Mauricio. Mauricio is one of our drives application specialists. He's an electrical engineer who has been working in the automation industry for more than 10 years. For the past 2 years, Mauricio has been working with us in the international sales department, supporting our colleagues in some European branches. Please welcome Mauricio and enjoy the presentation he has prepared for us.
Thank you, Leonardo. Hi, everyone. Thank you very much for joining us today here in this webinar. I hope everybody is safe and also healthy. And today I prepared here some advantages that we can have by using variable speed drives in pumping applications. So let's go to the presentation. All right. So here I prepared a little agenda for today's event. So it's best to know what we are going to talk about today. I have a small introduction talking about some statistics, how those pump systems works, type of pumps, pump and system curves. Then we are going to analyze the life cycle cost of a pumping system to then go to energy improvements and performance improvements that variable speed drives uh, can lead to your system. And then we will go finally to a solution and in the end, the questions and answer shot. Okay. Nearly 20% of world's electrical engineering is used by electric motors to run pumping systems. And also, we know that some pumping systems account for 25 to 50% of total electrical energy usage in certain industries. So before we start, let's go back to basics. Why do we need a pumping system? So a pumping system is designed to either move a fluid from one point to another or to circulate this fluid through a system to do some heat exchange. So let's get the marker here. So for example, thinking in a theoretical system curve of a pumping system where you just have to lead to the fluid from one place to a higher level place, we will have mostly static head into the curve system, which static head does not change with flow in the system. But if we think in a system that we just have to circulate this fluid, we will have mainly friction head, and friction head increase with the square of the flow. So of course, this is a theoretical curve, and in practical systems, we will have a combination of two, but some system will have more static head and less friction head, and the others will have more friction head and less static head. Less static head. Uh, so static head is a characteristics of the system, and it hardly can be minimized into the system. But friction head, we can minimize by improving the pumping systems, diminishing the length of the pipes and also the valves. And this is something we can do to improve pumping systems. And for a pumping system to work, we need to overcome the total system head of the system. And how do we do that? We do this with pumps. So then I'm not going extensively here talking about pumps, but pumps are mainly divided into dynamic pumps or displacement pumps. Dynamic pumps, there are also two groups, rotodynamic pumps, where we have the centrifugal pumps that we know a lot, but they also have some axial pumps and a mix of both. And of course, there is a single stage, multi-stage pumps, but yeah, not going all into these divisions. We have also special effect pumps that we call some jet pumps or reductors. And then we have displacement pumps where we have reciprocating movements with plunge, pistons, or even diaphragm pumps. And then we have rotary pumps that are progressive cavity for oil pumping, screw, gear, lobe, vane, peristaltic. We have a lot of variations. Okay, uh, talking about pumps and a little bit differentiation about them. Let's just generalize here. We have centrifugal pumps that usually we have this pump curve and we have the head and flow graph here. The pump curve will look like this. And then we also have diaphragm pump, positive displacement pump, where we have head and flow like this. Usually we also have this graph turned down. We're having the flow in the y-axis and the head in the x-axis. But here for comparison, we will have this way here. Uh, in a pumping system, we will have the system curve and also the pump curve. Where those two curves intersect each other, where they cross each other, we have the operating point of the pumping system. Let's go to the life cycle cost analysis of a typical pumping system. I'm making an assumption here that we have possibly three types of people watching this webinar. We have the curious ones that are here just for the knowledge, but we possibly have someone here with some pumping systems, a lot of costs into their pumping systems, and we possibly have someone here that works with pumps and perhaps want to have a solution more economic to offer to their customers. So let's analyze the life cycle cost of a total pumping system. Pumping systems, they usually works for 15 to 20 years. So initial costs, they are not a big part into these total costs. What we have mostly in costs are most energy costs during this life cycle. And we also have another bigger part here, which is maintenance cost, repair costs, and all related to this. So taking in consideration this, we should properly design the system in the beginning, perhaps investing a little bit more in the beginning to save more energy and to save with maintenance. So due to this, I'm going to divide this webinar now in two main parts, the energy improvements and also the performance improvements that can help with maintenance. Energy improvements are the most visible improvements that we can have in a pumping system by using variable speed drives. They are very tangible, and also it's easily to calculate how much you can save with energy savings by using variable speed drives, and that's why they mostly think of a variable speed drive saving energy. So considering that centrifugal pumps are the most popular pumps in the industry and that they have low cost, low maintenance, long operating life, and usually a tendency to be oversized. We we face some problems here. Uh, Reasons for oversizing centrifugal pumps. The designers usually have an uncertainty of how the system curve will be in final assembly of the system. That's why you have to oversize a little bit the pumps. Sometimes you also consider some future capacity into the system. And as this is all responsible, the designers are all responsible for this performance and they have to endure the uncertainties of the system, they tend to oversize the centrifugal pumps and other pumps as well, which leads us to inefficient pump operation into the operating point. That leads to energy waste and increased maintenance cost. Uh, Also, it leads to have an overflow or over pressure into the system. And to control this in a conventional system, we either use bypass valves or throttle valves. A bypass valve works in this way. Here we have a graph for head and flow in a system. And by using a bypass valve or a bypass system, a bypass circuit, we will reduce the flow of the system because we will have a bypass system working, and then we will also reduce the head of the system. Uh, this in this way we will change the system curve by adding losses to the system. So it's not an efficient way to do this. Also, by throttling the system, we will be changing the system curve. By changing the head, we will be changing the head of the system. And again, just adding losses to the system to control this overflow or overpressure that an oversized pump can bring to the circuit. Variable speed control method, it's the most efficient method to deal with this oversized system. When you have lower speed into the pump, you are imparting or adding less energy to the fluid. And this means no need to throttle the system or to bypass, which is just adding losses to the system. There are many speed variation methods into the market. There are either multiple speed pumps, and there are the adjustable speed drives, which they can be mechanical adjustable speed drives, hydraulic clutches, fluid couplings, and adjustable belts and pulleys. But then we have the electrical adjustable speed drives, air current clutches, wound rotor, motors controller, and the most popular ones into the industry, the variable frequency drives that are widely called variable speed drive. Let's get into the variable speed drive. How does a variable speed drive and how it can help in varying speed to a pumping system? So a variable speed drive, it's composed by three main parts. We have the rectifier bridge into the input, mostly 6-diode rectifier bridge. We have the DC link with the DC capacitors, and we have the inverter part with the IGBTs. So to start, we have the AC power supply going to the rectifier bridge. Then we rectify this, and also we have the capacitors to smooth this energy into this DC link. So having this very DC voltage into the link, we can use the IGBTs to switch this energy here and create a sinusoidal wave into the output. Variable speed drives, they consider a curve from voltage by frequency always constant, which leads to constant torque into the motor. And by varying the frequency of this sinusoidal wave into the output, we can vary motor speed. So always keeping the pumping system into the best efficiency point. Another important point to mention is that the variable speed drive will usually control a pumping system automatically by using a PID controller. We can always monitor the process variable, which can be flow, pressure, or other variable. And then we can set a control point into the system. And by adding proportional, integral, and derivative gains, we adjust the output of the drive, consequently the motor and the pump, to change the speed and change the process variable. These have a great impact in energy because if we take into consideration that this rotodynamic pumps follows the affinity laws, which means the flow is directly proportional to the speed of the pump, pressure is proportional to the square of the speed, and power is proportional to the cube of the speed. Uh, it means that imagine a pumping system for municipal water where at night you don't have to run at 100% flow, you just need 80% flow. This will mean that for those 8 hours at night you can save almost half of energy that you are going to waste in energy and have to be throttled or even bypassed. So this is the most efficient way to do this. Also, in low demand periods, the variable speed drive can either use one only auxiliary pump, a jockey pump. You can set to use a jockey pump instead of the main pump. And if the demand is too low, you can even put the motor to sleep and the pump to sleep and don't waste any energy at all until it requires you to increase the variable of the process. There are other improvements that a variable speed drive can provide to a system. They are often neglected because they are hard to calculate differently from energy savings that you can make some calculations. But we have a lot of performance improvements to provide to pumping systems with variable speed drives. To start, wear and tear in the equipment. All equipment into the pumping system are susceptible to wear and tear. Let's take into consideration the main parts here I selected. Valves. Valves are susceptible to wear and tear, and this can lead to leakages and also requiring constant maintenance. So if you find a leakage, sometimes a leakage it's a little bit normal if it's slow. If it's a small leakage into pumps or valves, but a huge leakage can lead to problems. Also, valves are always susceptible to overhauls. So controlling the pumping system by valves can add maintenance into your system and also constant overhauls into the system. Another part of the pumping system that it's very susceptible to wear and tear, it's pump bearings. For example, for rotodynamic pumps or centrifugal pumps, bearing life is proportional to the 7th power of speed, which means if we decrease the speed of the pump into a system that doesn't need to run at full speed all the time, and in average, if we decrease 10% speed of that system, it will increase the life, and the life of the bearing will be twice as much of the regular life of the pump bearing, and this can save you a lot in maintenance. Another part of the system that can also get some performance improvements by using variable speed drives is motors. By reducing speed, we can reduce average temperature into the motor and thus increasing lifetime of the motor. So speed reduction whenever it's possible is something that we can do with variable speed drives. With the PID controller, whenever you don't require to have much pressure or flow into the system, the variable speed drive will reduce the speed and avoid all those problems. Also, in a VSD system, we can switch operation in between the pumps to equalize the wear and tear of the pumps. So if it can keep monitoring the pumps and see how many hours it's working, so we can keep switching from one pump to another. Other common problems into pumping systems are water hammers that can lead to broken pipes and leakages. The water hammer effect is based on Newton's second law of motion, the conservation of momentum, that says that if a fluid is moving through a pipe and you tend to decelerate that fluid or even accelerate that, there will be a force. So imagine a pipe full of water running at 10 meters per second. If you try to stop that, will be a huge force into the system that can uh, lead to spikes into the pressure in the system, either low pressure or high pressure that can break the pipe or implode the pipe. This can lead to broken pipes, not only by water hammer, but broken pipes can happen for high pressure of, for example, trying to strangle a flow of a pumping system with a displacement pump, which can lead to a higher pressure into the system. And this all can happen and break your pulp, your pipe, your pumps and valves and other equipments to the system. And leakages are also a very huge problem in pumping systems. They can be simple leakages, leakages of clean water and normal fluids, or they can be toxic leakages in a wastewater treatment facility where you cannot have leakages of this water. The variable speed drive can present many functionalities to assist in this and avoid all those problems. For example, it can help with smooth pump and start and stop. So you can set some curves to start this pump slowly and smoothly to avoid the water hammer effect, and also decreasing the speed of the pump at the same height, so avoiding water hammer. And we can also have some broken and clogged pipe detection. By monitoring some variables into the process, we can see if the pressure is too high, and we can act to decrease this pressure or either shut off the valve or the pipe, the pump and the motor. Another huge problem, most common now into rotodynamic pumps, centrifugal pumps, are cavitation, internal recirculation, and for other pumps, dry running. So cavitation is a condition that happens at low pressure in the input of the pump and at a certain temperature. It can lead to the fluid to reach its vapor temperature, and then it can create some tiny bubbles of vapor into the system. These tiny bubbles, as soon as they try to leave the impeller, as the pressure will be increased, these tiny bubbles will be exploding, causing high velocity jets of water that can erode either the impeller and the pump volute, and this can lead to lower efficiency into the pump. Other problems, sometimes people don't speak about it, is internal recirculation. When you're running at low flow rate conditions, some parts of this fluid doesn't have enough energy to leave the pump, and it tends to recirculate inside the pump, which can also lead to erosion. And many pumps cannot try running, and this can be a problem, can damage the pump, can even break the pump, and you can have to perform some maintenance. To solve all of these, variable speed drives can present some protections. For example, variable speed drives can have anti-cavitation protection. It can analyze the input of the pump and check if the conditions of cavitation are appearing, so we can decrease the pump speed. Also, you can set some flow limits into the variable speed drive, and it can keep measuring the flow. You can limit the flow either a low level or a high level. And also, you can set some dry pump protections into the variable speed drive. It can be done either sensorlessly or also with some sensors. Another problem in pumping system, mostly in wastewater treatment plants, is the pump ragging and pump clogs. Pump ragging can happen when improper disposal into this system occurs. You have some rags or even very fibrous materials into the system that can start to accumulate into the pump impellers and can either clog completely the pump or can just decrease the efficiency of the pump by having some rags into the impeller. Also, variable speed drives can perform some deragging sequence into the pump by doing some rotational backwards and forward and try to take off all those rags. And this can clean the impeller and restore the pump efficiency. Let's go to a solution that can help you all. So, for example, here, I would like you to show a small video about the solution that we have here at WEG. Okay, that was the video. Uh, Guys, before we go forward, do you have any questions about the energy improvements that I presented and also the performance improvements, or even to some problems that happens with the pumping systems? Please put these questions into the chat. We will try to answer to you and also try to answer here live after the end of the presentation as well. Uh, Okay, going back to VEG Pump Genius, we have three modes as explained in the video. We have the simplex mode, the adds ideal features to variable speed systems with one pump or one pump and a jockey pump for low demand periods. There is also the multi-pump system, the best choice for cost-effective solutions that we can work with up to 5 pumps working via direct online start, soft starter, or other starting methods, and one pump being controlled by the variable speed drive. And for more accurately control of flow and pressure, the most complete solution is the multiplex solution. In this type of solution, we have one variable speed drive to every pump, and there is no need to any additional PLC, HMI, or any other devices, which can save you a lot of costs. The Pump Genius that we are explaining here, it's a free software available to VEG variable speed drives, and it can solve all those pumping problems that you can have in a pumping system, and also can leads to an improved system with less energy waste and also less maintenance or other costs into your system. Uh, it is a very user-friendly program that we have here, the WLP. We use this program to do the parameter setting of the drives and in the Pump Genius software. And also in this last part of this webinar, I'm going to share here a training suite case that I have, and I'm going to do the parameter setting of three functionalities from start to the end, and just to simulate how easy it is to use this program and how are the programming wizards as well. Uh, Now going, I have in the presentation here also how can you get all this program into our website, but let's go to the training suite case so I can show to you how we can do this. Let's open the WLP program. Once we can already put the training suite case here in the camera. I'm turning it on. Let's create a new project here from the start. Let's write down pump 1. Let's go for the CFW 500, the one I have here. To start, I'm in the camera here. Let's put the webcam, the auxiliary webcam here. All right, now you can see the training suite case. Okay, you probably can see my screen as well. I'm connecting the drive in the serial port. I think we have established communication. Let me just check if I am at the right port, communication 6. Okay, all right. First of all, we need to open the complete program here, Pump Genius. Let's do the simplex. Let's put it pump simplex. Okay, there will be a lot of screens here that I'm going to jump. We don't have time to read them all, but when you're doing at your own, I advise you to read them all. Let's, to start, download this program. We have all this ladder programming here into the software. We need to put this into the drive. Okay. Let me connect again. Communication 6. Okay. Okay, let's put the programming here into the drive. Compile. Okay. So I'll put in all this letter programming here into the drive, and then we can start playing with it. As I was saying, I'm going to present 3 functionalities, one at a time, because I don't have the dynamics of a complete pumping system here. I'm just having an analog input. So I will test them one at a time, but in a pumping system, you will be running with all protections at the same time. Okay, now the drive already has the programming there. We will be then starting to work with the wizards. Okay, again, not going to all these wizards here. You can set the ramps to start and stop. We can set the PID controller here, but let's go straight to the. I'm going to do dry pump, but first I want to disable the other functionalities here by putting 0, so we can see how the dry running will work. I don't want pipe charging. I don't want low level and high level right now. Let's go just for the dry pump. How does the dry pump functionality works? It detects that the pump speed is running at full speed, or we have a 60 hertz motor here and at very high speed. And if the motor torque is very low, it means that we don't have water into the system. So the standard value is 20, but for this training switch case, I'm going to put 15. Let's don't forget the time here for the protection to work. The others, we don't need to change anything. And these are all the parameters that we set values here into the wizards. Let's send these to the drive. Okay, drive has everything now. Let's open some monitoring screens so we can see what's going on in there. And okay, so here in the training bench, it's a little bit small to you, but you can see here in the drive, we have the set point, it's 20, the set point for the process variable, and we have the set point of the process variable is here. So this is the control set point, this is the process variable in the big number. And by changing the analog input here, I change the process variable. So I have some digital inputs here to simulate starting and stopping the motor. So let's start the motor and see what happens. So also in the screen here, you can see the motor speed is increasing. We are below the control set point, so the PID controller is running and we will go at full speed, as you can see. So let's simulate first this one here. So we are above the set point, and then what happens is the motor is running at the minimum speed. But if we go below the set point, it means we need to reach the control set point here of 20, and pump starts to speed up. And once we go over 54 hertz and the torque goes below 15, counter starts to count to 5. Then the fault happens. I will simulate again. Let's do it one more time. Motor is speeding up. The dry pump speed that we set is here, 54. Motor torque is here. We are below the control set point, and then torque is low, no water into the pipe, so protection happens and leaves you with no problems by dry running. So okay, this is one functionality I would like to show. Let me shut, let me turn off the drive and let's go try the others. Uh, First, let's disable the dry pump by putting 0. Okay. Let's try low level and high level here. Low level and high level depends on what you are, what process variable you are reading. It can mean pipe clog or even broken pipe if you're measuring pressure or flow. So let's put protection that will occur in 5 seconds. And let's send this all again to the drive. And okay, control set point is 20. We have low level at 10 and high level at 35. The maximum that we can put here is 40. So let's start the drive. We are above the low level and below the high level. Nothing happens. Motor is going to speed. And we are trying to reach the control set point by speeding up the motor at full speed. This is the PID controller happening. Let's open the monitoring screens here, low level and high level as well. So, okay, motor is speeding up. There is some clog into the pipe. It tries to slow the motor and the pump, but it's still the pressure is rising. So it counts to 5 and then shuts off the drive, the motor, and the pump. Let's try it again, one more time. Motor is speeding up. Still not high enough to so the high level can occur. And let's go above 35. As you can see, an alarm firstly, and then we will have a drive fault to indicate high level and possible clog into the pipe. Okay, let's reset the fault now and do the low level. We can also check the variable here. Motor is speeding up, trying to hit the control set point of 20, and the PID controller is working. And then if we go below 10, below the low level, which can lead us to internal recirculation to the pump, cause some erosion. We don't want that. So shut down the drive because some problem probably happened. Let's do it one more time. Motor is speeding up. Let's go below the set point. Perhaps we are measuring pressure here and the pipe is broken and we don't reach that low level, and then a fault occurs to indicate this broken pipe. And to finish, let me shut off the motor here. So to finish, let's do the last one. I saved the sleep and wake up mode to do in the last functionality. First, let's disable the low level and high level protection. And let's go back and do the sleep mode and wake up mode. So sleep mode will happen at the following situation. If PID controller it's working and even though you go at a very low speed for too many time, let's say 5 seconds, so lower speed in this system we set to be 40, so 42 is very low. And if the motor speed goes below 42 Hertz for 2 seconds, it will put the system to sleep. And how to wake up the system again? If we drop by 3 points the set point of pressure or flow that we set, that is 20 into the system, we will count to 5 and then we will wake up the motor again. Let's see how this works. Okay, let's put the control set point here. Let's open here. I see an alarm. Okay, okay, we need to drop 3 points to start the process. System is running at full speed, so let's think that the process variable goes over 20. That is our set point. Imagine at night in a municipal water treatment system, less people is getting water from the pipes, and then the set point goes below 20, motor starts to slow up, and as we go below 42 hertz for 5 seconds, it goes to sleep. If we decrease the process variable by 3 points, as we said, so as now 16, it starts to count to 5, and then wake up the motor again. You see motor starts running again. You can see also here speed of the motor. Let's make he goes to sleep again. PID controller is working, so motor speed is decreasing. Process variable is above the set point, so speed is decreasing. And once it goes below to 42, it will count to 5. The counter is starting again, and then goes to sleep. Let's drop the process variable a bit and see motor waking up automatically again. Yeah, that's it. It's all done into the training bench. Okay, let's go back here to the presentation. Okay, going back to the presentation. All right, so how do I use the Pump Genius? I have here, I'm going to share this presentation with you in a WeTransfer link, so you can have this material, so you can look again if you have any questions. But here you will see how you can get the WLP program and then to how to access the Pump Genius. If you have any questions about this process, you can also contact us. As you're here still, I would like to talk a little bit about WEG, our company. So our company is divided in 5 main business units, as you can see in the screen. So we have a motor business unit, we have an automation business unit that deals with these drives. We have transmission and distribution unit, energy unit, and coatings unit that covers all these products. Also, in automation, we have many divisions. We have the drives division that talks about soft starters and variable speed drives. We have the controls division, circuit breakers, control signaling, motor starters. We have machinery safety, building and infrastructure, critical power, electric panels, solar energy, electric mobility, and also digital business. And by having all these type of products, WEG is in the complete electric system by generating the power, transmitting this power, the usage in the industry, electric mobility, and construction technology. Also, we have a huge global presence. We have more than 30,000 employees worldwide, and we have 45 manufacturing sites in 12 countries. Also, We have commercial operations in 36 countries, distributors and agents in 120 countries, and sales into 125 countries. How you can get in touch with us? So to contact us, you can go to www.veg.net, sorry, www.weg.net, and then you can go for support, contact us, and then you can either send us a message here in the website, or you can look for the closest branch to you where you can have the address, where we can have the address. Okay. And we have the phone and email. Okay, now we are going to talk about our further webinars in this year. Okay, so this year we will still have two other webinars. One to talk about variable speed drives with integrated safety functionalities to optimize industrial machines. Diogo will be the speaker in this webinar, and it's going to happen in 26th of November. Check the time frame in your zone to see when this webinar is happening to you. Also, in 10th of December, we are going to have the webinar optimization for motor starters, longevity and energy savings for your application. And the speaker is going to be Rafael. Also, this invitation will comes to you the same way that this one came to you, via LinkedIn or even via email. And so keep posted, goes to our LinkedIn channel, follow us. And now we are moving to the Q&A chat. The presentation now it's over. We are just going to talk about the questions that we found here into the presentation. And let's see what we have here into the chat. I have some questions that someone just handed here to me, but let me take a look here in the chat. Okay, what is the difference between the sensorless dry pump protection and the broken pipe protection? Okay, so the dry pump protection, it will works the following. It will keeps monitoring motor speed and also the torque into the motor. So if torque is low, it means that we don't have water into the pipings, and motor is running at high speed with no water. We need to shut down the motor because it's dry running. The broken pipe, it's a little bit different. We will be watching motor speed. If it's running at a high speed and the process variable it's now reaching the set point still, it means that we have a broken pipe. There's a little bit difference between the two, but they all look similar. Let me see what other question I can find here. Okay, how do I select the correct VSD to my pump? This is a little bit complicated question. So first of all, the variable speed drive will be a consequence mostly of the motor and not to the pump itself. So as the motor is already properly sized to that pump, you will also need to check if the overloading capacity of this motor and this pump. If we can generalize a little bit, rotodynamic pumps usually have parabolic torque, so we can use normal duty overload capacity for the drives. And if we take into account the displacement pumps, they usually works with a constant torque. So then we should work with heavy duty overload capacity. How does the viscosity of the fluid influence in my VSD selection? Well, actually, the viscosity of the fluid will not going to influence in the VSD selection because the pump will handle the viscosity of the fluid, not actually the variable speed drive. Again, it's related to the application, but displacement pumps are more used to deal with high viscosity fluids, and usually they will be working with overload capacities higher than rotodynamic pumps. So then you should probably use a heavy duty overload capacity into your drive. Okay, here, just one more question before we finish. Do I have advantages in using variable speed drive and even in constant load systems? Yes, this sometimes people think that by having a constant load system into their pump system, they will not have savings anyhow, but this is not true. As we saw here today, we also provide some performance improvements by using variable speed drive. They are improvements in productivity, reliability into the system, wear and tear in the equipment are reduced. Also, you can save energy by reducing speed in some times. And yeah, this is something that we can achieve even in constant load systems. Recently, in June this year, the Northwest Energy Efficiency Alliance posted a white paper talking about some study that they made with 132 pumps in the Northwest region, and they also came to the same conclusion. So this is well proved that even in constant load systems, we can have some improvements using variable speed drives. Okay, that's all for today. Thank you so much. We will be sharing the link here still into the Q&A chat. You'll be possibly watching and seeing this link to access the PDF of the presentation and some other material. And don't forget to follow us on LinkedIn and also to subscribe to our YouTube channel. Thank you so much. Bye bye.